Wire a delicate electronic component directly to a raw power source like a battery, you won't get a working circuit, you'll get a tiny explosion. Electrical current is a heavy wave of kinetic energy. Without a mechanism to restrict it, a battery will shove as many electrons as possible through the path of least resistance until the internal wiring of your device simply breaks. To keep your hardware intact, you have to actively remove energy from the circuit before it reaches your most sensitive parts. Ohm's law states that voltage equals current multiplied by resistance. As this wide pathway constricts, the volume of flowing particles drops, but that kinetic energy doesn't disappear. As electrons hit the restrictive material, the energy transforms directly into heat. Getting rid of that heat safely depends on the physical size of the component. A larger surface area allows the resistor to expel more thermal energy into the surrounding air without overheating the core.
Designing safe electronics is an exercise in calculating exactly how much heat a circuit will generate and engineering physical pathways to bleed away. The most common way to build an electrical break is the carbon film resistor. Inside, it's just an insulating ceramic rod coated in a thin layer of carbon. To dial in the ohmic rating, a machine cuts a spiral groove through the carbon. This forces electrons to travel down a long, winding path. The physical flaw in this manufacturing process is the cut itself. The mechanical blade tears the carbon, leaving behind microscopic, jagged burrs along the edge of the trench. As electrons flow past these rough edges, they collide unevenly. This erratic movement generates current noise, random electrical interference that degrades delicate audio or measurement signals. For circuits that demand absolute precision, engineers swap the carbon out for a metal film resistor. The ceramic core is coated in a perfectly uniform, nanometer-thick layer of a metal alloy, like nickel chromium. Instead of a blade, a laser etches the spiral groove. It cleanly vaporizes the metal, leaving a razor-sharp edge where electrons flow without erratic collisions. This diagram compares 3 helical groove patterns to show exactly how geometry controls the resistance. A wide, short path lets electrons flow easily, but an incredibly thin path with heavy rotations restricts electron flow drastically, resulting in a much higher ohmic rating. Maintaining a pure electrical signal requires absolute physical consistency. The smoother the microscopic trench and the more uniform the material, the cleaner the output. Every resistor is built to handle a strict maximum power load. If you push an 8-watt surge through a tiny half-watt rated component, it rapidly exceeds its thermal capacity. The internal temperature spikes so fast the heat cannot escape. The core glows white, the outer layer catches fire, and the circuit is destroyed. Engineers also design reactive resistors that respond to their environment. A light-dependent resistor uses a layer of cadmium sulfide, where incoming photons of light physically dislodge electrons, dynamically lowering the resistance. Whether they are static metal films or reactive light sensors, traditional resistors are entirely passive. They react strictly to the immediate voltage or environment and retain zero data about what happened a second ago. Once the power shuts off, a standard resistor forgets everything about the electrical current that just passed through it. Overcoming that amnesia led to the creation of a 4th fundamental electronic component, the memristor. Looking at this chart plotting current against voltage, we see a figure 8 shape known as a pinched hysteresis loop. This curve proves the memristor alters its internal resistance based entirely on the volume of charge accumulated in it over time. That newly adjusted resistance state is locked in. Even when the power supply drops to 0, the device remembers its exact state. This physical behavior mimics a biological brain synapse. Just as neural pathways in our brains grow stronger and more efficient the more we use them, the memristor adjusts its conductivity based on its own electrical history. Replicating this biological structure in hardware paves the way for neuromorphic computing, ultra-dense arrays that process data at very low power. By merging the ability to restrict flow with the capacity to remember, the memristor evolves the resistor from a simple electrical break into the physical hardware required for artificial intelligence.